4 kilometers below the surface of the modern Pacific, a research submersible drops into darkness. The last sunlight disappeared 40 minutes ago. The water temperature outside the hull sits at just above freezing. The pressure pressing against the titanium sphere is 400 atmospheres, 400 times the weight of the air around you right now, sitting wherever you're sitting. If the hull failed, the people inside would not drown. They would be crushed into a space smaller than a coffee mug in less than a second. The pilot turns on the external lights, and the lights reveal a world. Not a graveyard. Not an empty plain. A living world, populated by creatures that seem to have no business being alive at all. Giant isopods the size of small dogs, scuttling across the sediment on armored legs. Tube worms 2 meters long, clustered in pale forests around volcanic vents. Anglerfish drifting past the viewport, their lures pulsing with a light that no creature on the surface has ever seen with its own eyes. But here is what most people do not understand about that world. The animals drifting past that viewport, the isopods, the tube worms, the anglerfish, the blind white shrimp, the ghost octopi curled in folds of rock. Their lineages have been down here for a very, very long time. Longer than mammals. Longer than the first fish ever pulled themselves onto land and learned to breathe air. Longer than some of the continents you live on tonight. The deep sea is the oldest continuous habitat on Earth. The grasslands are new. The rainforests, by geological standards, are new. Even the oceans themselves have risen and fallen dozens of times, flooding continents, then retreating to expose the bones of ancient seafloors. But the deep has always been here. Cold, dark, crushing, patient. And if you could somehow travel back through time while remaining at that depth, if you could press some impossible button and watch the same square kilometer of ocean floor through the last 500 million years, you would see things that most people do not know existed. You would see armored predators larger than cars, with jaws that sheared bone. You would see sharks whose lower jaws contained spirals of teeth, rotating outward like saw blades. You would see oceans that turned the color of rust, oceans that turned the color of dried blood, oceans whose surfaces boiled with hydrogen sulfide while everything below suffocated in silent darkness. You would see extinctions so total that only one species in 20 survived. You would see life recover, rebuild, experiment with new body plans, fail, try again. Tonight we are going to descend. Not just in space, but in time. We are going to start at the surface, where the sunlight hits the water, and we are going to drop. Slowly, methodically, past the zones where modern divers can safely reach. Past the zones where sunlight penetrates. Past the zones where most fish live. Past the zones where most people have ever heard of. And at every depth, at every darker layer of water, we are going to pause. And we are going to ask the same 2 questions. What used to live here? And this is the part that will keep you listening. What might still? Because here is the truth about the deep ocean that even most biologists do not fully appreciate. We have mapped the surface of Mars in higher resolution than we have mapped the floor of our own sea. We have sent more humans to the moon than we have sent to the deepest parts of our own oceans. The Hadal Zone, the trenches that plunge below 6 kilometers, covers an area roughly the size of Australia, and the number of human eyes that have ever looked down into it is smaller than the number of people who have been president of the United States. Something could be down there right now, something we have not yet found, something whose lineage is older than every tree on the surface, something whose ancestors survived every mass extinction, something that has been waiting. That is what this descent is about. That is the world we are visiting tonight. So before we begin, take a moment to like this video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments how deep you personally would be willing to dive if someone handed you a submersible and the key. I always find the answers fascinating. There are people who say 20 meters and mean it. There are people who say the bottom of the Mariana Trench without flinching. The difference between those two answers tells you something important about a person. Now, dim the lights if you haven't already. Get comfortable. Close your eyes if you want to. You will not miss anything visual, because most of what I am about to describe takes place in a world where there is nothing visual to miss. Take a deep breath. Let the modern world fade away. Let your mind sink. This is a descent, and it is going to take a while. The discovery that prehistoric oceans were full of monsters is itself a strange story, worth telling briefly, because it explains something important about why we trust the reconstructions you are about to hear. For most of human history, nobody suspected that oceans had a history at all. Ancient Greek philosophers wrote about the sea as something eternal, unchanging, the same water that their grandfathers had sailed on, and the same water their grandchildren would sail on. The idea that the sea itself had a past, that there had been oceans where there were now mountains, and mountains where there were now oceans, did not exist in any coherent form until the 17th century, when a Danish scientist named Nicholas Steno noticed something that did not add up. Steno had been studying the teeth of sharks on the Mediterranean coast when someone brought him a set of strange stone teeth found embedded in rocks far inland, hundreds of kilometers from the nearest coastline. The stone teeth matched the shark teeth almost exactly in shape. But they were stone, and they were in solid rock in a hill, nowhere near any water. Steno's conclusion was quiet, careful, almost hesitant but revolutionary. The rocks, he wrote, had once been the bottom of the sea. The teeth had belonged to sharks that had lived there. The shape of the land itself could change. Water could become stone. Stone could rise into mountains. Time was deeper than anyone had imagined. It took almost 300 more years to fill in the details of that early insight, but Steno's observation became the seed of an entire science. Geology, paleontology, paleoceanography, the study of oceans that no longer exist. And it turned out, as later scientists began peeling back the layers of ancient seabed preserved in continental rock, that Earth's oceans had been home to a parade of creatures so strange, so terrifying, and so completely different from anything alive today, that reconstructing them would occupy paleontologists for generations. The fossils came first, then the chemistry. Isotope ratios in marine limestone told scientists the temperature of ancient seawater, sometimes to within a single degree. Trace metals revealed whether those seas had been rich in oxygen or suffocatingly anoxic. Microscopic fossils, foraminifera, radiolarians, tiny single-celled organisms with shells of silica or calcium carbonate, preserved snapshots of ocean currents that had flowed before any mammal existed. Entire books' worth of ecological information could sometimes be read from a single cubic centimeter of ancient mud. By the middle of the 20th century, Paleoceanographers had begun to assemble a picture of the world's past oceans that was, in many ways, more detailed than the picture of the world's past forests. Forests decay. Leaves rot. Wood burns. But the seafloor, when conditions are right, preserves almost everything that falls onto it. A fish that sinks into deep, oxygen-poor mud can be preserved so perfectly that its last meal is still visible inside its stomach. A squid can leave behind the ink it released in panic 300 million years before you were born. A jellyfish, a creature with no bones, no shell, nothing hard at all, can sometimes leave a ghost, an impression in fine silt, a faint curved shape that scientists can still identify as a jellyfish 250 million years later. This is how we know. This is why we can speak with confidence about creatures that went extinct before the first dinosaur. We are not guessing. We are reading the stones. And the stones, when you know how to read them, tell a story that is much, much stranger than you were taught in school. Start with a simple number. Life has existed on Earth for approximately 3.8 billion years. For most of that time, roughly the first 3.2 billion years, all of it was confined to the water. The land was dead. Bare rock, sand, dust blown around by winds across empty continents. For billions of years, if you had stood on any beach on Earth, you would have heard only waves. No birds, no insects, no rustling grass. The land was silent because nothing lived there. The oceans, meanwhile, were busy. Very busy. We will never fully reconstruct those earliest seas. The rocks that would contain their fossils have been recycled too many times by plate tectonics, subducted back into the mantle, melted, reformed as new rock. The oldest reliable fossils of complex life come from about 600 million years ago, in formations like the Ediacaran Hills of South Australia, where the fine sandstones preserve the impressions of creatures so strange that paleontologists spent decades arguing about whether they were animals at all, or plants, or something entirely different that no longer has any living descendants. Some of the Ediacaran organisms looked like quilted mattresses. Others looked like fronds. Others looked like discs, like bags, like disturbing geometric patterns. They had no mouths. They had no eyes. They had no digestive systems anyone has ever been able to identify. They absorbed nutrients directly through their skin, drifting in warm, shallow seas under a sun that was slightly dimmer than today's. They were the first ecosystem of large, complex life that the ocean ever produced. And then, about 540 million years ago, something happened that changed everything forever. The Cambrian explosion. It is called an explosion because, in the fossil record, it looks like one. For hundreds of millions of years, the oceans had been quiet, populated by soft-bodied drifters with no teeth, no claws, no armor, no predators. Then, across a geological interval so brief that we cannot resolve it in most rocks, everything changed. Eyes appeared. Teeth appeared. Shells appeared. Legs appeared. Every major body plan of modern animal life, and many that no longer exist, emerged within a span of perhaps 20 million years, an instant in geological terms. The oceans filled with predators. And this is where our descent begins. Because the first creature we are going to meet, drifting through the warm surface waters of a Cambrian sea 500 million years ago, is not friendly. It is not soft. It is not quiet. It is watching you with compound eyes that contain more than 16,000 lenses. And it is hungry. The first 200 meters of any ocean is called the sunlit zone, or the epipelagic zone, or more poetically, the photic zone. It is the only part of the ocean where photosynthesis can occur. It is where almost all of the planet's marine life is concentrated today, and it is where almost all of the planet's marine life has been concentrated for the entire history of complex life on Earth. If you could time travel to any point in the last 540 million years and drop into an ocean, the sunlit zone is where you would find the most action, the most predators, the most prey, the most strange experiments in biological form. Because the sunlight is what drives the food chain, and the food chain is what drives evolution. And so the top 200 meters of ocean has always been where the pressure was highest and the selection was most intense. Set your mental submersible to the Cambrian, 508 million years ago. The continents you know from modern maps do not exist in recognizable form. North America and Greenland are joined, sitting roughly on the equator. Europe is a separate landmass. Africa and South America and Antarctica and Australia are welded into a single southern supercontinent called Gondwana, drifting through what will one day be the Atlantic Ocean. The water temperature at the surface is warm, somewhere around 25 degrees Celsius, because the planet is in a greenhouse phase with no polar ice. You descend to a depth of 20 meters. The sunlight is bright above you, filtered into a wavering gold green. The water is thick with life, but life of an unfamiliar kind. There are no fish. Fish will not evolve in recognizable form for another 50 million years. There are no squid, no octopi, no whales, no dolphins, no seals, no turtles, no crabs. None of the animals you think of when you think of an ocean are there. What is there is stranger. Trilobites crawl along the seafloor below you in the tens of thousands. Some are the size of a coin. Others are as large as dinner plates. Their armored bodies are built in 3 lobes, hence the name, and their compound eyes, already sophisticated, are among the earliest true eyes in the fossil record. They are the Cambrian's equivalent of a cockroach, incredibly successful, incredibly abundant, and destined to thrive for almost 300 million years before their lineage finally ends. Above them, drifting through the water column like a slow-moving airship, is the predator we mentioned at the end of the last chapter. Its name is Anomalocaris. And if you have never heard of it, you should understand that the name means, literally, strange shrimp, because when the first fossils were discovered, they were so bizarre that paleontologists assumed they were looking at some kind of shrimp-like creature. It took almost a century to realize that the pieces they had been cataloging as several different animals were actually parts of a single enormous predator. Anomalocaris was about 1 meter long. That may not sound enormous by the standards of later ocean monsters, but in Cambrian terms, it was gigantic, the apex predator of its age, the largest animal on Earth. Its body was segmented, flanked by rippling side flaps that let it swim with a wave-like undulating motion. At the front of its head were 2 large grasping appendages, like armored arms, lined with spines. Its mouth was a circle of interlocking plates, like a tightening aperture, capable of pulping shells. And its eyes were perched on stalks, and each eye contained more than 16,000 individual lenses. For context, a modern dragonfly has about 30,000 lenses, and a dragonfly is famous for having the best vision of any arthropod alive today. Anomalocaris, more than 500 million years ago, was already seeing the world in higher resolution than almost any invertebrate that has ever existed since. It was a visual hunter. It watched. It tracked. It calculated distance. In the sunlit Cambrian seas, it was the nightmare that trilobites learned to hide from. Picture it for a moment. You are drifting in warm, clear water. The light from above is fractured into shifting gold patterns on the seabed. A trilobite scuttles across the sand below you. And then from the edge of your vision, a shadow glides in 1 meter long, segmented, its side flaps rippling like a slow heartbeat. Its 2 grasping arms reach forward. Its stalked eyes rotate toward you. The 16,000 lenses are processing your shape, your distance, your speed. It is deciding whether to eat you. This was the ocean 500 million years ago. Warm, bright, and ruled by something that looked like nothing else that has ever lived. Anomalocaris was not alone. The Cambrian seas were full of experiments. Apobinia had 5 eyes on its head and a long grasping proboscis that ended in what looked almost like a claw, a creature so bizarre that when its discoverer first showed his reconstruction to a scientific meeting, the audience laughed. They thought it was a joke. It was not. Hallucigenia, as the name suggests, was so strange that paleontologists originally reconstructed it upside down and backwards. When the error was finally corrected, what had once looked like a nightmare on stilts became merely a nightmare on a different set of stilts. Wiwaxia was a crawling oval of overlapping scales, armored like a miniature tank. Marella, the most common fossil from the Burgess Shale of British Columbia, had 4 long spines sweeping back from its head and resembled nothing alive today. And here is the thing about the Cambrian that most people never fully grasp. The Cambrian seas were not just the early version of our seas. They were a different ocean entirely, a parallel biosphere populated by body plans that were tested, that worked for tens of millions of years, and that then vanished. If evolution had rerun the tape, the oceans we know today would be unrecognizable. Vertebrates, the group that includes fish, and therefore everything that descends from fish, which includes you, were a marginal lineage in the Cambrian. Small, unimpressive, a minor footnote. The dominant animals were arthropods and their relatives. If any one of the minor Cambrian lineages had won the long evolutionary game, the oceans of today would be full of creatures we can barely imagine. We tend to think of evolution as a progression toward modern forms. That is almost entirely wrong. Evolution is a process of experimentation, and most experiments fail. The Cambrian was an age of experiments, and most of those experiments did not make it to the next chapter of Earth's history. But enough did, including one small, soft-bodied, eel-like creature called Pichia, which had a stiffening rod running down the length of its body, a precursor to what would, 400 million years later, become a spine. Pichia was 2 inches long. It was not important in the Cambrian Ocean. It was, in fact, almost completely invisible beside the giants. But it carried inside its small body the architectural blueprint that would eventually build fish, and then amphibians, and then reptiles, and then mammals, and then, eventually, the species capable of making the documentary you are listening to right now. That is how close it was. Our entire lineage in the Cambrian was a worm smaller than a paperclip, drifting in the warm shallows while Anomalocaris ruled the open water. But the warm shallows were not where the strangest part of the Cambrian Ocean lived. You have to go deeper. You have to leave the sunlight. Below 200 meters, the light begins to fade. Blue becomes dominant. Red disappears entirely. The water grows colder. And in the Cambrian, just as today, there were already creatures that preferred it that way. We will meet them next. Between 200 meters and 1,000 meters of depth, there is a region that oceanographers call the Twilight Zone. Some call it the Mesopelagic. The light that reaches it is so dim that no photosynthesis can occur. Plants cannot live here. Most plankton cannot live here. What reaches this depth is a slow, continuous snow of dead material falling from the sunlit zone above. Bits of dead algae, dead zooplankton, flakes of decomposing fish, fecal pellets. Marine biologists call it marine snow, and it is the food source that supports almost every creature living in the twilight zone of the modern ocean. The creatures of the twilight zone are adapted to darkness. Their eyes are huge, often tubular, designed to catch every scrap of light that filters down from above. Many of them produce their own light, bioluminescence, using it for communication, camouflage, hunting, mating. The twilight zone is the realm of the hatchetfish, of the lanternfish, of the cookie-cutter shark, of the vampire squid. It is one of the strangest biomes on modern Earth. It was one of the strangest biomes on prehistoric Earth, too. And in the Ordovician period, 470 million years ago, the Twilight Zone was ruled by something truly enormous. Set your mental, submersible to the Ordovician. Descend through the sunlit zone. Watch the light darken from gold to green to a dim blue-gray. At around 300 meters, the surface above is just a faint glow. At 500 meters, it is almost entirely dark. And here, at 500 meters in an Ordovician sea, you would be in the hunting grounds of an animal called Camarosras. Camarosras was a cephalopod, a relative of the modern squid and octopus, but it looked nothing like either. Its body was housed inside a straight, conical shell that could reach, according to some estimates, more than 10 meters in length. Other estimates are more conservative, closer to 6 or 7 meters, but even the conservative estimates describe an animal larger than a modern great white shark, with its body armored inside a tapering spear of shell. From the wide end of that shell, a head emerged. Tentacles waved. 2 large eyes, adapted to the dim twilight, scanned the water. At the center of the tentacles was a sharp, parrot-like beak, the same kind of beak that modern octopi and squid used to tear apart their prey. Camarosras was the apex predator of the Ordovician oceans. It hunted by hovering at depth, using jet propulsion to move through the water slowly and silently, its 10-meter shell trailing behind it like the fuselage of a small airplane. When prey came within reach, the tentacles shot out, grabbed, pulled the victim toward the beak, and the beak did the rest. There is an old reconstruction, popularized by a BBC documentary some years ago, that depicts Camarosras attacking the first sea scorpions, the earliest sharks, even early jawed fish, and dragging them back into its shell to consume them. Whether that reconstruction is entirely accurate is debated. But the evidence suggests that Camarosras and its relatives, the orthocone nautiloids, as they are known, dominated the open water and the twilight zone of the Ordovician seas for tens of millions of years, occupying the same ecological role that later whales and sharks would fill. Try to picture it in the dim blue-black water of an Ordovician twilight zone. You are drifting at 500 meters. The light from above is just enough for your eyes to register barely. The water is silent. And then out of the darkness, a long dark shape glides past you 10 meters long, a spear of living shell, moving with a slow, calculated grace. Its eyes turn toward you. Its tentacles unfold. And then it decides you are not worth the effort, and it drifts on into the dark. That is the Ordovician twilight zone. That is what was hunting down there 470 million years ago. But Camarosras was not the only predator in the Ordovician seas. Above it, in the sunlit zone, a new kind of animal was beginning to diversify. The Eurypterids, sea scorpions, arthropods like trilobites, but much, much larger and much, much more dangerous. By the late Silurian period, about 420 million years ago, one species of Eurypterid, Eucalopterus rhenaniae, had grown to 2.5 meters in length, making it the largest arthropod ever to have existed. Larger than any crab, any lobster, any spider that has ever lived. A sea scorpion the size of a small car, with pincers as long as a human arm. And here is the part that people often miss about the Eurypterids. They did not stay in the ocean. Some species, the later ones, began to experiment with freshwater, with estuaries, even with brief excursions onto dry land. The fossil record preserves trackways, parallel lines of clawed footprints in ancient mud that show Eurypterids walking across Silurian beaches, possibly mating, possibly hunting, possibly simply moving from one pool to another. For a moment, more than 400 million years ago, the largest land animals on Earth were sea scorpions longer than grown men. They did not stay on land. Nothing backbone could challenge them there yet, because nothing backboned had learned how to breathe air. But in the shallow Silurian seas, they were the terror of the coastline. Imagine a moonlit beach more than 400 million years ago, and imagine something 2.5 meters long, covered in armor, dragging itself across wet sand, leaving a trackway that a paleontologist would find 40 generations of ape evolution later. That is the image you should carry with you as we descend further. Because the ocean was about to produce something even worse. In the Devonian period, beginning around 419 million years ago, a new lineage of predators rose. And they were the first great armored monsters of the sea. They were called placoderms. And one of them, a species called Dunkleosteus, is the reason you should never, ever swim in a Devonian sea. The Devonian period is sometimes called the Age of Fishes, because during its 70 million year span, fish diversified into forms so varied, so dominant, and so ecologically successful that they took over every niche in the oceans. By the end of the Devonian, fish would rule the seas the way dinosaurs would later rule the land. They would produce giants. They would produce specialists. They would produce predators whose bodies were built like war machines. But before the sharks and the ray-finned fish took over, there was another lineage. The placoderms, armored fish, creatures whose front halves were sheathed in bony plates fused into solid shields, with a flexible, scaly back half trailing behind like an afterthought. And the largest of them was Dunkleosteus terrelli. Let me give you the specifications. Dunkleosteus was approximately 6 meters long, with some estimates going up to 9 meters for the largest individuals. It weighed between 1 and 4 tons. It had no teeth in the conventional sense. Instead, its jaws were lined with 2 pairs of sharp, beak-like bony plates that sheared against each other like industrial shears, self-sharpening with every bite. Studies of the jaw mechanics have calculated that Dunkleosteus could open its mouth in about 1/50th of a second, creating a suction that would pull prey in before the prey even knew it was being attacked. Its bite force has been estimated at roughly 8,000 pounds per square inch, greater than a great white shark, comparable to a Tyrannosaurus rex, and sufficient to shear through the armored shells of almost any other animal in the Devonian Sea. There is a detail about Dunkleosteus that makes it particularly terrifying if you think about it for too long. It had no peers. There was no bigger predator in the water with it. For 10 million years, Dunkleosteus and its close relatives were the absolute top of the food chain. Nothing challenged them. Nothing ate them. The only thing that killed a Dunkleosteus was old age, disease, or another Dunkleosteus. And indeed, the fossil record preserves several specimens with bite marks from other Dunkleosteus, suggesting that, like many apex predators, they were cannibalistic. Picture the Devonian Sea, 370 million years ago. You are floating at about 30 meters of depth. Sunlight streams down through warm tropical water. The seafloor is covered in early coral reefs, in the bodies of trilobites, in the shells of ammonoids and nautiloids, in the waving fronds of early seaweed. Schools of early jawed fish, small, agile, only a few centimeters long, dart through the water around you. It looks peaceful. And then the water darkens. A shape passes overhead. It is 8 meters long. It is covered, from its head to the middle of its body, in a bony helmet of overlapping plates. Its face is blank, featureless, except for 2 eyes and a massive beak-like jaw. It is hunting. When Dunkleosteus struck, the mechanics were brutal. The jaw opened in a fraction of a second. A pulsive suction pulled the prey forward into the mouth. The bony shears closed. There was no chewing, no mouthing. The prey was simply cut in half, or crushed, or sheared into pieces small enough to swallow. Dunkleosteus did not need to chase. Dunkleosteus ambushed. It hung in the water, as motionless as its heavy armored body allowed, and waited for a school of fish to pass. Then it exploded forward with one violent lunge, and it ate whatever it could get. The Devonian was the age when this happened in every sea on Earth. But the Devonian was also the age when something quieter, and ultimately more important, was happening in the shallow coastal waters. A group of lobe-finned fish, ancestors of a group that would eventually give rise to amphibians, reptiles, birds, and mammals, were learning to survive in the brackish zones where rivers met the sea. Their fins were stout and muscular. Their air bladders were connecting to their throats in a way that would eventually become lungs. They were not escaping onto land because land was more attractive. They were escaping because the Devonian Ocean was so full of armored death that the tidal mudflats, the swamps, the half-drowned forests, the places where even Dunkleosteus could not follow, were suddenly the safest neighborhoods on Earth. That is the irony, the quiet paradox, that sometimes gets lost in the story of how life conquered the land. Life did not conquer the land because the land called. Life conquered the land because the ocean was trying to kill us. Every bird singing in every forest today is descended from a fish that fled Dunkleosteus. But the Devonian was not going to end gently for the armored giants. About 358 million years ago, at the Devonian Carboniferous boundary, something went wrong with the oceans. Oxygen levels dropped. Temperatures swung. A series of extinction pulses, spaced over a few million years, wiped out the placoderms, most of the early jawed fish lineages, entire reef systems, and approximately 75% of all marine species. The cause is still debated, possibly a combination of volcanic activity, changing sea levels, the rise of the first forests on land pulling carbon out of the atmosphere and cooling the planet, and the resulting collapse of ocean oxygen. Whatever the cause, the Devonian extinction ended the age of placoderms forever. Dunkleosteus disappeared. The great armored predators were gone. And into the ecological vacuum they left behind, a new kind of predator began to rise. Sharks. The Carboniferous and Permian seas that followed the Devonian were full of sharks, but sharks that were not like modern sharks. They were weirder. They were, in some cases, genuinely surreal. And the strangest of them all had teeth arranged in a spiral inside its lower jaw, like the blade of a circular saw. Its name was Helicoprion, and nobody is entirely sure how it ate. By 330 million years ago, in the middle of the Carboniferous period, the oceans were recovering. Coral reefs had rebuilt themselves from new lineages. The trilobites, survivors of every previous crisis, were still trundling across the seafloor, though in reduced numbers. The cephalopods had diversified into coiled ammonoids, which would become one of the most successful groups of marine animals in Earth's history, persisting for another 280 million years before finally going extinct alongside the dinosaurs. And the sharks, or the early cartilaginous fish that we call sharks, had begun a radiation that produced some of the most bizarre body plans ever seen in a vertebrate. Modern sharks, with their familiar torpedo shapes and rows of triangular teeth, are actually a relatively late and conservative design. The early sharks tried everything. Some had spines projecting from their heads like unicorn horns. Some had rows of teeth fused into bony plates. Some had teeth arranged in spirals. Some had teeth arranged in saws. Some had modified teeth that grew out of the tops of their heads, apparently for mating displays or for holding onto mates during reproduction, in ways that are still debated. The Paleozoic ocean was, in many ways, the golden age of weird shark design. Set your submersible to 280 million years ago. Late Carboniferous. The supercontinent Pangaea is assembling, grinding the old continents into a single landmass, closing seaways, changing ocean currents, altering climate. The sea level drops. Warm shallow seas shrink. Extinction pressures rise. In these troubled waters, the strangest shark of all time evolves. Helicoprion was a shark-like fish, roughly 3 to 4 meters long, with one feature that has baffled paleontologists for more than a century. Its lower jaw contained a spiral of teeth. Not a row, not a set, a spiral. Up to 150 sharp teeth, arranged in a tight coil, curling inward. The oldest teeth were at the center of the spiral, worn and dull. The newest teeth were at the outside, sharp and ready. As new teeth grew in, the old teeth rotated inward and were eventually discarded in the center of the coil. For more than 100 years after the first Helicoprion fossil was described in 1899, nobody knew how the spiral sat inside the animal's mouth. Some early reconstructions placed the spiral on the shark's snout, curling outward like a decorative ornament, Some placed it on the shark's back, like a bizarre dorsal fin. Some placed it at the tip of the tail. The problem was that the spiral is the only part of Helicoprion that fossilizes well. The rest of its body was cartilage, which rarely survives. So, for a century, paleontologists were reconstructing an entire animal based on its teeth alone. In 2013, a team led by Leif Tapanila used CT scanning to examine a Helicoprion fossil that preserved more than just the spiral. What they found resolved the mystery. The spiral sat inside the lower jaw, along the midline. When the mouth closed, the outer edge of the spiral sliced through prey like a rotating saw blade. The older teeth at the center of the coil held prey in place. The newest teeth at the outside did the cutting. Helicoprion was, effectively, a shark with a buzzsaw in its mouth. Picture it hunting in the Carboniferous twilight. A school of ammonoids, shelled cephalopods resembling nautiluses, drifts through the water. Helicoprion approaches from below, its spiral jaw held open. It strikes. The spiral rotates. The ammonoid is sliced cleanly in two, its soft body caught between the teeth, the shell spiraling away into the darkness. The shark closes its mouth and swallows. For tens of millions of years, this worked. Helicoprion and its relatives thrived. They survived the end of the Carboniferous. They survived the early Permian. They were successful, widespread, ecologically important. And then, about 252 million years ago, the oceans of Earth underwent something so catastrophic, so thorough, that the word extinction does not quite capture what happened. The Permian-Triassic boundary extinction. The Great Dying. 96% of all marine species vanished. Let me read you that number again, slowly. 96% of all marine species vanished. This is not a typo. This is not hyperbole. This is the actual, quantified estimate from the paleontological record. At the end of the Permian period, 252 million years ago, something happened to Earth's oceans that came closer to sterilizing them than any event before or since. 19 out of every 20 marine species died. The coral reefs died. The ammonoids almost died. Only a handful of species survived, and from those survivors, the entire later ammonoid lineage re-radiated. The trilobites, which had persisted for nearly 300 million years through every previous crisis, finally died. Forever. The Paleozoic ocean ecosystem, which had been evolving and diversifying since the Cambrian, was effectively terminated. It took roughly 10 million years for marine life to recover to anything resembling its previous diversity. 10 million years of mostly empty seas. What happened? The leading hypothesis, supported by growing evidence, involves the Siberian traps. This was one of the largest volcanic events in Earth's history. Not a single eruption, but a sustained outpouring of lava that lasted for about 2 million years and covered an area roughly the size of Western Europe in basalt kilometers thick. The volume of magma erupted is estimated at more than 4 million cubic kilometers. For perspective, the 1980 eruption of Mount St. Helens produced about 1 cubic kilometer of ejecta. The Siberian traps produced about 4 million times that much, spread over 2 million years. But it was not the lava that killed the oceans. It was what the lava did to the atmosphere. Massive volcanic eruptions release enormous quantities of carbon dioxide and sulfur dioxide. The Siberian traps pumped these gases into the atmosphere on a planetary scale. The atmospheric carbon dioxide levels skyrocketed. The planet warmed. Global temperatures rose by perhaps 8 to 10 degrees Celsius. And as the surface waters of the ocean warmed, their ability to hold dissolved oxygen decreased. Because warm water holds less oxygen than cold water. That is simple chemistry. The warming oceans began to suffocate. But there is worse. As the surface warmed and stratified, ocean circulation collapsed. The deep ocean, which normally gets oxygen through the slow overturning circulation driven by temperature differences, stopped getting any new oxygen. The deep became anoxic. Without oxygen, the bacteria that live in deep water began to metabolize differently. They began producing hydrogen sulfide. Hydrogen sulfide is poison. It smells like rotten eggs. It is what your digestive system produces when something goes badly wrong. And in high enough concentrations, it kills essentially everything that breathes oxygen. In the late Permian, the oceans of Earth filled with hydrogen sulfide. It began at the deep seafloor, then rose through the water column as the anoxic layer expanded upward. At the surface, the hydrogen sulfide would have bubbled into the air, killing land animals near the shore. Some evidence suggests the atmosphere itself may have become temporarily toxic. The oceans, viewed from orbit, would have turned a sickly purple-green color as photosynthetic sulfur bacteria bloomed in the oxygen-free water. Life in the Permian oceans was not killed by one thing. It was killed by everything at once. Heat, acidification, anoxia, hydrogen sulfide, collapsed food webs, failed reproduction. Every system that marine life depended on failed simultaneously. And in the deep, in the place we have been slowly descending toward throughout this episode, the silence became absolute. For something like 2 million years, the deep ocean was a zone of almost total chemical hostility. Nothing breathed. Nothing moved. The sediment that was laid down during this interval, when it is found in modern rocks, is often black, stained by organic material that should have been consumed by scavengers but was never touched because there were no scavengers. The bodies of dying surface creatures sank into the dark and were simply preserved. Sometimes intact, sometimes in vast mats, a carpet of death covering the seafloor across entire continents' worth of ancient ocean basin. Try to hold that image in your mind as we sink deeper on our descent. The deep Permian Sea. Warm, acidic, oxygen poor, filled with drifting clouds of hydrogen sulfide, carpeted in the unburied corpses of a dying biosphere. Silent. And then, and this is the part that is, in its own way, the creepiest detail of all, slowly, over millions of years, life came back. It came back strangely. The survivors were not the dominant species of before. They were weeds, survivors, generalists, extremophiles. They radiated into the empty niches. They rebuilt from almost nothing, an entirely new ocean ecosystem. And the oceans that emerged from the Triassic recovery were no longer the oceans of the Paleozoic. They were something different, something with a new cast of characters. Reptiles would enter the water for the first time. And from those reptiles would come the true sea monsters. The kind that filmmakers have been trying and failing to accurately recreate on screen for decades. Creatures that grew larger than any predator fish ever did. Creatures whose eyes were the size of dinner plates. Creatures whose jaws were wider than a human being is tall. The Mesozoic oceans were coming. And in those oceans, the ecological niches that had been left empty by the Permian extinction would be filled, not by fish, but by something that had gone back to the water to hunt. About 250 million years ago, in the early Triassic period, the oceans began to recover from the Great Dying. The recovery was slow. For the first few million years, marine ecosystems were dominated by disaster species, small, fast-reproducing generalists, the equivalents of weeds, filling empty niches because nothing else was there to compete. But over time, biodiversity rebuilt. And as it rebuilt, something strange began to happen on the coastlines. Some of the reptiles that had survived the extinction on land began, gradually, to return to the sea. This is worth pausing on. Life had taken 350 million years to crawl out of the ocean, develop lungs, develop 4 limbs, develop dry skin, adapt to terrestrial conditions, diversify into amphibians and then reptiles. All of that hard-won evolutionary work, all of those adaptations for life on land, had taken hundreds of millions of years to develop. And now, within a few million years of the Permian extinction, some of those very same reptile lineages were abandoning land and going back. Why? The answer is ecological opportunity. The seas after the extinction were full of empty niches. The apex predators were gone. The large-bodied fish lineages were reduced to fragments. Anything that could exploit those empty niches would inherit an ocean full of prey with no established predators. The reptiles that returned to the sea were, in a sense, invading. And they had an enormous advantage: they breathed air. In an ocean whose deep waters were still recovering from the extinction, where oxygen levels in some regions were still dangerously low, air-breathing predators could hunt where fish could not. The first wave were the ichthyosaurs. Picture a Triassic sea, 240 million years ago. The water is warm, shallow, tropical. The coasts are lined with early reef ecosystems. And gliding through the shallow water, moving with the smooth, undulating motion of a dolphin, is an ichthyosaur. Not a fish. A reptile. Its body is streamlined, its limbs fused into flippers, its tail tipped with a vertical fin. Its eyes are enormous, among the largest eyes in proportion to body size of any vertebrate that has ever lived. The largest of the early ichthyosaurs was a genus called Shanosaurus, and some specimens from a controversial species called Shanosaurus sigonensis reach lengths of more than 20 meters. That is longer than a modern school bus. That is longer than most sperm whales. That is the size of a small blue whale. And this was an ichthyosaur, a reptile, cruising through the Triassic seas more than 200 million years ago. How did it get so large? The answer seems to be abundance. The Triassic oceans, recovering from the extinction, were populated by enormous blooms of squid-like cephalopods called belemnites, which swam in vast schools. An ichthyosaur that could swim through those schools and filter or gulp down belemnites, by the thousand could grow to almost any size that its body plan would support. Shanosaurus appears to have been a specialist on this food source, its teeth reduced to fit small, soft prey, its body enlarged to take advantage of near-unlimited food. But Shanosaurus was only the beginning. the ichthyosaurs would diversify across the Jurassic and Cretaceous periods, producing hundreds of species, most of them smaller and faster than Shanosaurus, many of them hunting fish and smaller cephalopods in the open ocean, and some of them the eyes. Let me tell you about the eyes. A Jurassic ichthyosaur called Temnodontosaurus had eyes that measured roughly 25 centimeters in diameter. The largest vertebrate eyes ever documented from any animal, living or extinct. The only thing that comes close is the eye of a modern giant squid, and giant squid eyes are comparable precisely because they are solving the same problem: how to see in the twilight zone, in water where almost no light penetrates. Temnodontosaurus hunted at depth. It dove, probably to depths of 500 meters or more, into the cold dark of the Jurassic twilight zone, and it hunted whatever was down there. Imagine the scene. You are drifting at 400 meters of depth. The sunlight from above is just a faint gray glow. You are in the Jurassic twilight zone, 180 million years ago. And out of the darkness, a shape appears, 10 meters long, streamlined reptilian. Its flippers beat slowly. Its tail propels it through the water. And its eyes, each the size of a dinner plate, are fixed on something that you cannot see. It does not see you. It is not interested in you. It is interested in whatever is hiding in the darkness below. That is the Mesozoic twilight zone. That is what was diving down there. But ichthyosaurs were not the only predators in the Mesozoic seas. Alongside them, and often larger, were the plesiosaurs. Plesiosaurs are the creatures that most people picture when they imagine a sea monster. Their body plan is famously strange: 4 enormous flippers, a compact barrel-shaped body, and either an extraordinarily long neck or an extraordinarily massive head. Some plesiosaurs had necks that were longer than their bodies, with more than 70 individual vertebrae. Some had short necks but heads that were more than 3 meters long, containing teeth as long as kitchen knives. The short-necked, big-headed plesiosaurs are called pliosaurs, and they were the apex predators of the Jurassic seas. The largest of them, a species called Plesiosaurus funke, sometimes informally nicknamed Predator X by the researchers who excavated it on Svalbard, is estimated at 12 to 15 meters in length, with a skull more than 2 meters long. Its bite force, based on jaw mechanics, has been estimated at up to 33,000 pounds per square inch, which would make it one of the most powerful bites in the history of life. That is stronger than Tyrannosaurus rex. That is stronger than Megalodon. The bite of Plesiosaurus could crush a small car. Plesiosaurus hunted ichthyosaurs. It hunted smaller plesiosaurs. It hunted giant fish. It hunted almost anything else in the sea. And when it was hungry, there was nothing in the Jurassic Ocean that could escape it by being too big or too heavily armored. Picture it. You are floating in clear Jurassic water, perhaps 50 meters down. Sunlight streams through in shafts. A school of fish parts in front of you. And then from the deeper water, from the blue darkness below, a head rises. 2 meters long. 20 centimeters of teeth exposed. Eyes the size of soccer balls. The head moves slowly, then with sudden acceleration, and the rest of the body follows, 4 massive flippers pulling a body 15 meters long through the water. It passes beneath you, a dark submarine of muscle and teeth, and it continues on its way. You are not its prey. You are too small. The Mesozoic oceans were full of these giants. As the Jurassic gave way to the Cretaceous, ichthyosaurs declined, but new lineages rose to replace them. The mosasaurs, giant marine lizards, relatives of modern monitor lizards, diversified across the late Cretaceous seas. The largest, Mosasaurus hoffmanni, reached lengths of 17 meters, with a serpentine body and a mouth full of curved, recurved teeth designed to hold struggling prey. Mosasaurs were ambush hunters, lurking just below the surface, striking upward at turtles, fish, seabirds, and even other mosasaurs. Cannibalism among mosasaurs appears to have been common. And in these same seas swam Xiphictinus, a bony fish 6 meters long with a mouth full of tusk-like teeth and a habit of swallowing prey whole that was, frankly, too large for him. Several Xiphictinus fossils have been discovered with the complete skeletons of other large fish still preserved inside their stomachs, prey that they had swallowed, but that had killed them by piercing some vital organ from the inside. The fossil is called the fish within a fish, and it is one of the most famous vertebrate fossils ever discovered. That image, a predator killed by the last thing it tried to eat, preserved together for 70 million years, two skeletons nested inside each other, captures something essential about the Mesozoic ocean. It was an ocean of ambition, an ocean of predators who tried things. Some of those things worked. Some of those things killed them. But all of it, all of the Mesozoic madness came to an end. 66 million years ago, the asteroid you heard about in another documentary struck the Yucatan, and the Mesozoic oceans collapsed. The ichthyosaurs were already gone by then, having declined slowly for the previous 30 million years. But the plesiosaurs, the mosasaurs, the giant predatory fish, the great Cretaceous ammonites, all of them vanished in a geological instant. And the oceans that came afterward, the oceans of the Cenozoic, were different. They were the oceans we are still living in. They were the oceans that would produce, in time, the deepest creatures we are about to meet. Because we are still descending. We have been talking about the shallow and middle waters this entire time. We have not yet reached the real deep. The midnight zone is waiting. Below 1,000 meters of depth, the last traces of sunlight disappear completely. No blue remains. The water is black, not dark black, the kind of black that human eyes cannot fully comprehend because human eyes have never evolved to deal with total, unbroken, absolute absence of light. The temperature is barely above freezing. The pressure is 100 atmospheres and rising with every additional 10 meters. This is the midnight zone, the bathypelagic, the realm of eternal darkness. And here is the thing about the midnight zone that makes it crucial to understanding the history of life on Earth. The midnight zone has been the same for roughly 500 million years. The surface of the ocean has changed dramatically, warming, cooling, flooding continents, dropping to expose the bones of ancient shorelines. The twilight zone has changed almost as much. But the deep has remained, in its basic physical characteristics, the same. Always cold, always dark, always high pressure, always dependent on whatever falls from above. And because the environment has been so stable, the creatures that live there have been, in many cases, the most conservative lineages in the animal kingdom. The deep sea is where the living fossils hide. The deep sea is where lineages that went extinct on the shallow shelves, or in the sunlit zone, sometimes persist, forgotten, overlooked, surviving in the dark. We are going to talk about those lineages in a few chapters. But first, let us talk about what prehistoric midnight looked like. because the midnight zone of a prehistoric ocean was not empty. It had its own cast of characters. Most of them are known only from fragments, because the deep sea preserves fossils poorly. The carbonate saturation horizon, the depth at which calcium carbonate begins to dissolve in seawater, sits at around 4 kilometers in most modern oceans, and bones that sink past that depth often dissolve before they can fossilize. But fragments exist, and the fragments tell a story that is stranger than almost anything we have seen on the shallower levels. Consider the giant squid. The modern giant squid, Architeuthis dux, reaches lengths of more than 13 meters and lives almost exclusively in the midnight zone. Its eyes are the size of dinner plates. It has 8 arms and 2 long feeding tentacles, the latter tipped with barbed suckers that can grip prey so tightly that the suckers leave circular scars on the skin of sperm whales, the only predator that reliably hunts giant squid in the deep. But giant squid are not new. Cephalopods have been swimming in the deep for more than 400 million years. The lineage includes the orthocones we met earlier, the ammonoids, the belemnites, and eventually the modern squid. And somewhere in that long lineage, in the deep of the Mesozoic or early Cenozoic, there were giant squid-like animals of which we have only traces. Beaks, isolated hooks from their tentacles, impressions in fine-grained sediments, enough to know that the midnight zone of the Jurassic was already home to large, soft-bodied predators that hunted in complete darkness. How did they find their prey? The same way modern deep-sea cephalopods do. Bioluminescence, vibration, specialized sensory systems that detect the faint electrical fields generated by living bodies. The deep sea has always been a world of non-visual senses, and the animals that live there have always been, in a sense, tuned to frequencies that surface creatures cannot perceive. Now imagine that world, in the middle of the Cretaceous, 90 million years ago. The surface of the ocean, hundreds of meters above, is dotted with the carcasses of dead fish, dead ammonites, dead mosasaurs. The dead sink. Slowly over hours and days, the bodies drift down through the water column. Scavengers wait at every depth. Smaller fish and cephalopods tear pieces off as the body falls. By the time the carcass reaches 2,000 meters, only the bones remain. Those bones settle onto the seafloor in the eternal dark. And then something finds them. Deep-sea sharks, hagfish, isopods the size of dogs, amphipods, small shrimp-like crustaceans, swarming the carcass by the thousands, eating it from the inside out. This exact ecological process is happening in the modern ocean right now tonight, while you listen to this. It has been happening for hundreds of millions of years. Every whale, every shark, every large fish that has ever died in the open ocean has eventually fed the deep. The deep is a slow-motion garbage collector. It processes the remains of everything that dies above. And occasionally, very occasionally, the deep produces something that rises back to the surface to be seen. In 1938, a fishing trawler operating off the coast of South Africa pulled up, among its catch, a strange fish. Blue, heavy, about 5 feet long, with fleshy, lobed fins that looked almost like the beginnings of legs. The captain of the trawler had never seen anything like it, so he contacted a local museum curator, a woman named Marjorie Courtenay-Latimer, who came to examine the fish. She recognized it immediately. She also refused to believe what she was seeing. It was a coelacanth, a lobe-finned fish from a lineage that was supposed to have gone extinct at the end of the Cretaceous, 66 million years ago, alongside the dinosaurs. Every fossil of a coelacanth that had ever been found was from rocks older than 66 million years. The coelacanths were ancient history. They were a footnote in vertebrate paleontology, interesting mostly because they were related to the lobe-finned fish that had eventually given rise to tetrapods, to amphibians, to reptiles, to us. They were supposed to be dead. And here was one, freshly caught in 1938. The coelacanth lineage, it turned out, had not gone extinct at the end of the Cretaceous. It had simply retreated to the deep, to caves and overhangs on the steep underwater slopes off East Africa and Indonesia, at depths of 200 to 700 meters, where no paleontologist had ever thought to look for it. The coelacanth had been hiding for 66 million years. It was still there. It is still there now, in the twilight zone of the Indian Ocean, a living fossil older than the Himalayas. That discovery, more than any other in the 20th century, changed how biologists think about the deep ocean. Because if the coelacanth could survive, unnoticed, for 66 million years in habitat we had barely explored, what else might be down there? The short answer is, we do not know. The longer answer is, probably a lot. And this brings us, finally, to the deepest zones of the ocean. The zones where the water is so deep, so cold, so pressurized, that even most modern research submersibles cannot reach them. The zones where, if anything has been waiting, it has had a very long time to wait. We are going deeper. At 4,000 meters of depth, the water temperature stabilizes at approximately 2 degrees Celsius, just above freezing. The pressure is 400 atmospheres. The darkness is total and has been total for more than 3 kilometers of water above you. Sound does travel at this depth. In fact, sound travels better in cold, dense water than in warm water, but most of the sounds are not biological. They are geological. The low grumble of the seafloor shifting, the crack of undersea landslides, the deep moaning of water masses sliding past each other. Occasionally, from great distances, the calls of whales. Those travel thousands of kilometers in the deep sound channel, and they are heard down here. This is the abyssal zone, the floor of most of the world's oceans. It covers by area more of Earth's surface than any other habitat, more than all the deserts, forests, grasslands, mountains, and tundras combined. The abyssal plain is the largest continuous environment on the planet, and we have mapped less of it than we have mapped Mars. And it has been here, more or less in its current form, for hundreds of millions of years. This is important for understanding what we are about to discuss, because the abyssal zone preserves lineages that have been refined by 400 million years of selection for life in total darkness, at near freezing temperatures, under crushing pressure, with food sources consisting almost entirely of whatever happens to sink from the zones above. Who lives down here? In the modern ocean, a surprising amount. Cold-adapted sharks, including the Pacific sleeper shark, which can reach 6 meters in length and hunts in water so cold that most fish would freeze to death. Giant tube worms up to 3 meters long, growing around hydrothermal vents, entire ecosystems powered not by sunlight but by chemical energy from the Earth's interior. Snailfish, which have been observed and filmed at depths of more than 8,000 meters, making them the deepest dwelling vertebrates known. Grenadier fish, lanternfish, glass sponges, some of which may live for more than 10,000 years without moving, slowly filtering water. What about prehistoric abyssal life? The fossil record is thinner here than in the shallows. For the reasons already discussed, deep-sea bones dissolve before they fossilize. But what evidence we have suggests that the abyssal zone has been continuously inhabited since at least the Ordovician, and possibly earlier. Trace fossils, preserved burrows, occasional exceptional fossil deposits where unusual chemistry allowed preservation. What we know for certain is that the deep ocean has been a refuge. When the shallow oceans suffered their catastrophes, the Endordovician extinction, the Devonian extinctions, the great dying of the Permian, the End-Triassic, the End-Cretaceous, the deep ocean suffered less. Not nothing, but less. The abyssal lineages were partly protected by their habitat. Cold water holds more oxygen than warm water. Deep water is buffered against rapid chemical changes by sheer volume. The deep was, repeatedly, the place where lineages hid and waited for the surface to recover. And sometimes, when the surface did recover, the deep sent up surprises. Consider the frilled shark, Chlamydoslechus anguineus, a living species, alive today, caught occasionally by deep-sea fishing operations. It looks like something drawn by a child who has been told to draw a shark, but has only seen pictures of eels and dinosaurs. Long serpentine body, frilled gill slits like ragged collars, a mouth full of three-pronged teeth that curve inward, so that any prey grabbed by those teeth cannot easily pull away. Its lineage goes back at least to the Cretaceous, possibly further. The frilled shark has been hunting in the deep for at least 80 million years, barely changed. Or consider the goblin shark, Mitsucurina ostoni, another living species, but one whose lineage goes back 125 million years. Its jaw is hinged unusually, allowing it to be projected forward from the skull in a single explosive motion, a feature so strange that the first biologists to see footage of a goblin shark feeding assumed they were looking at some kind of imaging error. The goblin shark lives in the deep, eats whatever it can catch, and has been doing exactly this for more than 100 million years. Or consider the Greenland shark, Somniasis microcephalus, a cold-water, deep-water shark that can reach lengths of 7 meters. A 2016 study using radiocarbon dating of Greenland shark eye lenses. The eye lens is one of the few tissues in the body that does not metabolically turn over, estimated that some individuals were more than 400 years old. 400. Some of the Greenland sharks alive in the North Atlantic tonight were born before the United States existed, before Shakespeare wrote his first play. They have been swimming slowly in cold, deep water for 4 centuries, and they may live for another century or 2 before they die. The deep, in other words, is full of things that are very, very old. Individuals that are older than any human who will ever live. Lineages that are older than any ecosystem we see on the surface. And because the environment has been so stable, because the pressures that drive rapid evolution in shallow water are absent here, the deep-sea fauna is, in many cases, essentially unchanged since the Mesozoic. Swim through a modern abyssal plain, and you are swimming through the Cretaceous. You are swimming through a preserved ecosystem. You are swimming among creatures whose ancestors, in nearly this same form, watched the mosasaurs die above them, watched the first whales descend into the darkness tens of millions of years later, watched every single thing on the surface come and go. They have been patient. But even the abyssal zone is not the deepest part of the ocean. Below 4,000 meters lies a small, specialized environment that covers only a tiny fraction of the seafloor, but that houses, in some cases, the strangest and most isolated communities of life on Earth. The trenches. The Hadal Zone. Below 6,000 meters. The deepest water on the planet. That is where we are going next. The Hadal Zone is named after Hades, the Greek underworld, the place where the dead go. It is the deepest part of the ocean, defined as anywhere below 6,000 meters. It consists almost entirely of trenches, long, narrow gouges in the seafloor where one tectonic plate is sliding beneath another. The Mariana Trench in the western Pacific is the deepest. Its lowest point, the Challenger Deep, sits at approximately 10,935 meters below sea level. That is deeper than Mount Everest is tall. If you inverted Everest and dropped it into the Challenger Deep, the peak of the mountain would still be more than 2 kilometers below the surface of the sea. The pressure at the bottom of the Challenger Deep is approximately 1,086 atmospheres. That is more than 1,000 times the pressure you feel right now, sitting where you are. A styrofoam cup taken down to that depth and retrieved returns the size of a thimble, compressed by the pressure. Human lungs exposed to that pressure would not survive. Titanium research submersibles require walls 80 millimeters thick to descend there safely. Only a handful of human beings have ever been to the bottom. The first, Jack Pickard and Don Walsh, reached it in 1960 aboard the bathyscaphe Trieste. They stayed for 20 minutes. The viewport cracked slightly during the descent. They ate chocolate bars while they looked out at the seafloor. They saw, to their considerable surprise, a flatfish swimming past them at 10,911 meters. That observation, which some marine biologists doubted at the time, has since been confirmed. The Hadal Zone is inhabited. It is not empty. Life, somehow, has found its way even into the deepest trenches on Earth and figured out how to survive there. Hell, the key challenge at Hadal depths is not actually the cold or the darkness. Those are the same as in the abyssal zone above. The key challenge is the pressure. At more than 1,000 atmospheres, the basic chemistry of life becomes difficult. Proteins fold differently under high pressure. Cell membranes behave differently. Enzymes that function fine at shallower depths stop working. Even water itself behaves slightly differently under such extreme compression. And yet life is there. Snailfish, amphipods, strange worms, microbes in staggering diversity. Every expedition to the Hadal Zone, and there have only been a handful, has returned with new species that were previously unknown to science. Some of them have been unknown at any level, meaning they belong to entirely new evolutionary groups not represented anywhere in shallower waters. The Hadal Zone of the modern Pacific, in other words, contains animals that are genuinely alien to the rest of Earth's biosphere. How old are these lineages? This is one of the hardest questions in deep-sea biology, and the honest answer is, we often do not know. The Hadal ecosystems of different trenches appear to be partially isolated from each other, meaning that each trench contains endemic species found nowhere else. This suggests that the Hadal fauna has been evolving in situ for a long time, possibly tens of millions of years, possibly longer. Some of the snailfish lineages in the Mariana Trench have been estimated to be at least 20 million years old, having diverged from their shallow water relatives roughly during the Miocene. Which means, if we take a conservative interpretation of the evidence, the hadal fauna has been down there, in those specific trenches, evolving in near-complete isolation, since before there were whales as we recognize them, before there were modern dolphins, before the last glacial cycle even began. Life forms adapted to a pressure environment that no human can tolerate, in a habitat that no human eye has seen except in brief glimpses through the armored viewports of a handful of submersibles. Now take the deepest interpretation. Some researchers have argued that certain hadal microbial lineages may go back to the origin of life itself, that the hadal zone, like the deep subsurface of the Earth's crust, may be a refuge where microbial lineages from the Archean Eon, 3 billion years ago or more, may still persist, unchanged, in a habitat that has not changed in 3 billion years either. That is speculation. It is not confirmed, but it is also not impossible. And if it is true, then the hadal zone contains some of the oldest continuous lineages of life on Earth, older than the oxygen atmosphere, older than multicellular organisms, older than almost anything on the surface except the continents themselves. Picture it now. You are sitting in a submersible, 45 minutes into your descent to the floor of the Mariana Trench. The external pressure has just passed 1,000 atmospheres. The viewport is a 4-inch thick dome of reinforced acrylic. Outside the viewport, the water is so cold and so dark that if the lights failed, you would experience sensory conditions that no surface organism has ever evolved to tolerate. Not human, not any vertebrate, not any land animal of any kind. The pilot turns on the lights. Outside the viewport, a small white fish drifts past. It is a snailfish. It is adapted to pressures that would compress your skeleton. It has lived here, or its ancestors have, for longer than the genus Homo has existed on Earth. It pays you no attention. It has no reason to. It is simply going about its life, in the deepest water on the planet, as its species has done since before humans came down from the trees. And beyond the light's reach, beyond what you can see, is the rest of the hadal zone, stretching for kilometers in every direction, carpeted in soft sediment that has been accumulating for millions of years, punctuated by brief disturbances when something large dies on the surface and eventually, weeks or months later, sinks to the bottom to be consumed by the waiting scavengers. That is the bottom. That is as deep as the ocean goes. But we are not done yet, because there is one more place to visit. One more zone that most people do not even know exists. Below the sediment, below the basement rock, deep inside the crust of the planet itself, there is a biosphere. And it may be the oldest habitat of life on Earth. When drilling crews cut cores of rock from deep beneath the seafloor, they find something that used to be considered impossible. They find life. Living microorganisms. Bacteria. Archaea. Single-celled organisms embedded in the solid rock, surviving on chemical energy extracted from the minerals around them, metabolizing at speeds so slow that some individual cells may not divide for thousands of years. The deep subsurface biosphere, the zone of life that exists inside the rocks of the crust, sometimes kilometers below the bottom of the ocean, may contain, by total biomass, as much or more life than all the surface ecosystems of Earth combined. This is still a frontier of biology. The numbers are uncertain. The estimates range widely. But the rough calculation is that the deep subsurface biosphere may contain something like 15 to 20% of all living biomass on Earth. An enormous hidden ecosystem living in rock, eating rock, breathing rock. How long have they been there? Some of them may have been there forever, or more precisely, since the origin of life. Some researchers have argued that life first evolved not in a warm tidal pool, as the old textbook story goes, but in exactly these environments, deep, hot, chemically energetic rocks around hydrothermal vents. If that hypothesis is correct, then the subsurface microbial ecosystems we are finding today are not recent invaders of the deep rock. They are the original life. They are the direct descendants of the first cells. They have been there continuously for more than 3.5 billion years. That is longer than the oceans, as we know them, have existed. That is longer than plate tectonics in its modern form has existed. The subsurface microbes are older than nearly everything, and they are vast. Samples from boreholes on continental crust, kilometers below the surface of the land, show microbial communities. Samples from the ocean floor, drilled several kilometers into the sediment, show microbial communities. Samples from volcanic rock beneath ancient ocean basins, samples from groundwater deep within Precambrian shield rocks, samples from the very deepest places scientists have managed to drill, all of them show life. Strange life. Slow life. Life running on chemical energy that has nothing to do with sunlight or the surface of the planet. Picture a bacterium right now, embedded in basaltic rock, 2 kilometers below the floor of the Pacific. The rock around it formed when lava erupted from a mid-ocean ridge and cooled in seawater 40 million years ago. The bacterium arrived in the pore spaces of that rock, swept in by circulating seawater, and it has been there ever since. It is part of a community. The community extracts hydrogen from the reaction between seawater and olivine. It uses the hydrogen as an energy source. It lives. It does not die. It may not even divide on human timescales. It just persists. An individual bacterium, 2 kilometers beneath the ocean floor, may outlive entire human civilizations without taking a single bite of food by any definition that a surface organism would recognize. This is the world below our world. This is the biosphere beneath the biosphere. And here is the part that, I think, should genuinely keep you up at night, except we have agreed that tonight you will sleep, so let me say it carefully and gently. Every other habitat we have visited on this descent has had catastrophes. The surface has been frozen, baked, acidified, glaciated, bombarded by asteroids. The midnight zone has suffered during the great extinctions. The abyssal plain, though buffer, has experienced slow changes as ocean chemistry shifted. Even the Hadal zone has been altered over geological time by shifting tectonic plates and changing ocean currents. The deep subsurface has been through almost nothing. The rocks around those microbes have been the same rocks, with the same chemistry, producing the same energy, for tens of millions to billions of years. Whatever extinction events happened on the surface did not reach down there. Whatever climate changes altered the oceans did not touch them. The subsurface biosphere is the most stable, most continuous, most preserved environment on Earth. If there is a single lineage of life on this planet that has survived, unbroken since the very beginning, since the first cells, 4 billion years ago, the subsurface biosphere is where it would be. and it is where, based on current evidence, some researchers strongly suspect it is. When we say the deep is old, this is what we mean. Not old in the sense of a fossil. Not old in the sense of a preserved record. Old in the sense of still alive. Continuously alive. Alive right now, tonight, while you listen to this, in a darkness deeper and longer than anything the surface world contains. That is the deepest the descent goes. That is the bottom of every analogy. Below the sediment, below the rock, a living world that the sun has never touched. And from there, let us begin our slow ascent back up. Before we surface, we need to make one more stop. Because the idea that we have been following throughout this descent, that the deep is old, that lineages persist in it that have been lost elsewhere, that the ocean is a museum of deep time, leads to a specific, unsettling conclusion. Some of the creatures from the prehistoric oceans we have been discussing are still alive. Not their descendants, modified by millions of years of evolution into something unrecognizable. Them, or rather, their species or near species, preserved with such fidelity in the stable, deep environment that a biologist looking at them today is looking at something that has barely changed since the Mesozoic. Sometimes earlier, we have already met some of them. The coelacanth, surfacing in 1938 after being presumed extinct for 66 million years. Its lineage goes back 400 million years. The living coelacanth is not the same species as any fossil coelacanth, strictly speaking. But its body plan, its anatomy, its behavior, its ecology, all of these are recognizably, directly, unmistakably ancient. When you look at a coelacanth, you are looking at a fish essentially unchanged since the Devonian in its essential nature. You are looking at a creature that swam in the same seas as Dunkleosteus. The frilled shark, 80 million years old as a lineage, still hunting in the deep. The goblin shark, 125 million years old, still extruding its strange jaws to catch prey in the dark. The Greenland shark, lineage uncertain but possibly very old. Individuals alive now that were born in the 1600s. The horseshoe crab. This one we have not mentioned yet, but it is worth mentioning. The horseshoe crab is not actually a crab. It is not an arthropod closely related to crabs. It is a chelicerate, a member of the group that includes spiders and sea scorpions. The horseshoe crab lineage goes back 450 million years. Some of the fossil species are, anatomically, almost indistinguishable from the living species crawling on the Atlantic coast tonight. The horseshoe crab is, in the most literal sense, a living Ordovician animal. You can walk along a beach in Delaware and watch creatures whose ancestors were alive before the first fish had jaws. The nautilus, living cephalopod with an external spiral shell, extremely similar to its ammonoid cousins who went extinct with the dinosaurs. The nautilus lineage is more than 500 million years old. There are 6 living species, all in tropical Pacific waters, all hunting in the twilight zone, all preserving a body plan that was already ancient when the first mammals evolved. The giant squid. As a species, we do not know exactly how old, because its fossil record is effectively non-existent. Squid do not fossilize well, because their only hard parts are the beak and the thin internal pen. But as a body plan, giant squid-like cephalopods have been around since at least the Jurassic, and possibly much earlier. The giant squid hunting a sperm whale in the deep Atlantic tonight is participating in an ecological drama that has been played out, in one form or another, for 100 million years. The hagfish, an eel-like jawless fish, a relative of the lampreys, and possibly the oldest living vertebrate lineage on Earth. Hagfish fossils from more than 300 million years ago are almost identical to living hagfish. They secrete enormous quantities of slime when threatened. They feed on the carcasses of dead fish by burrowing into them. They are frankly disgusting. They have also been doing exactly what they do for longer than vertebrates have had limbs. All of these are living fossils. All of them are still out there tonight. Some of them are in the deep. Some of them are on the beach. But all of them represent the same principle. The ocean preserves. The ocean remembers. Lineages that you would assume were long dead are still present, often unnoticed, often in environments that we have barely explored. And this raises a question that I want to leave you with before we begin the final ascent. What else has been preserved? Because here is the thing about the deep. We have explored so little of it. The Hadal Trenches, almost untouched. The abyssal plain, mapped at low resolution, biologically sampled in only a few locations. The Midnight Zone, vast beyond imagining, visited only in brief bursts by research submersibles. And even the Twilight Zone, which is closer to the surface and easier to reach, still produces new species with almost every deepwater expedition. What else is hiding? We know some things that should exist, based on the fossil record and the reconstructions of ancient oceans, but that have never been observed in the modern deep. Some plesiosaur-like body plans, some unusual cartilaginous fish, some unusual cephalopods. Most of these are probably extinct. Probably. But the word probably is doing a lot of work in that sentence, and the deep is a place where the word probably has turned out to be wrong before. The coelacanth showed us that. Every biologist working before 1938 would have told you, with complete confidence, that the coelacanth lineage was extinct. They were wrong. They were wrong by 66 million years. What are we wrong about now? We do not know. That is the honest answer. We do not know what is down there. We do not know what has been waiting. We only know that, given how little of the deep we have explored and how effectively the deep preserves old lineages, it is almost certain that there are species alive tonight, in the Midnight Zone or the abyss or the trenches, that would astonish us if we ever managed to find them. The history of the deep ocean is not finished being written. It is still being written every night in the dark. Let us ascend. Slowly, the way you would in a real submersible, pausing every few hundred meters to allow your perceptions to adjust, to pressurize and depressurize correctly, to avoid the physiological problems that rapid ascents cause. Slowly through the Hadal Zone we have just left, the bottom of the ocean at its deepest. Up through the abyssal plain, across an environment the size of a continent, dark and cold, and inhabited by things older than forests. Up through the Midnight Zone, where the giant squid hunt and the lanternfish glow. Up through the Twilight Zone, where the last light of the surface begins, faintly, to return, a deep blue-gray glow that you had almost forgotten existed. Up into the sunlit zone, past 200 meters, past 100 meters. The light becomes golden, then bright, then almost painful after so long in the dark. A fish flashes silver beside you. A turtle passes overhead, silhouetted against the brightness. You break the surface. Air, wind, the smell of salt. A horizon in every direction. The sky enormous blue, impossibly bright. Seabirds crying overhead. The sound of waves. You are back. You have returned to the surface world. The same world you started in. The world where humans walk, where cities exist, where trees grow. Everything we have discussed tonight is still there, still happening, kilometers below your feet. But you cannot see any of it. The surface is opaque. The deep is invisible from above. And here is the feeling I want to leave you with as you drift towards sleep. Almost everyone who lives on Earth lives in a thin skin of reality. We see the surface of things. We live in a two-dimensional slice of the three-dimensional world. The atmosphere above us extends upward for 100 kilometers before it thins to space. The crust beneath us extends downward for 30 or 40 kilometers before the mantle begins. The oceans, where they exist, add another 3 kilometers on average to the habitable column. In total, the zone of life on Earth is a sphere of staggering dimension, most of which is invisible, most of which is unexplored, most of which contains creatures and processes we have never observed. And the deep ocean is the largest, most continuous, most ancient slice of that zone. Hundreds of millions of cubic kilometers of cold, dark water, stable for hundreds of millions of years, inhabited by lineages older than everything on the surface. When you stand on a beach, the waves you hear are the topmost 0.1% of an ocean that goes much, much deeper than you can easily imagine. The water touching your feet is in contact, through an unbroken column of fluid, with the bottom of the Mariana Trench. Everything down there, everything we have spent this documentary describing, is connected to the water you feel when you swim. That is the ocean. That is what the ocean is. And here is the thought that should, in some quiet part of your mind, stay with you even after you forget the specifics of this documentary. You have never been in an ocean. You have been in its skin. You have been in its sunlit upper layer, its thin, warm crust, the zone where the light reaches and where the familiar fish swim. The real ocean, the one that extends downward for kilometers, the one that covers more of Earth than all land combined, the one that has been home to life since before there was a functional atmosphere on the surface. That ocean you have never touched. Almost nobody has. It is still there tonight. It is still dark. It is still cold. It is still full of things we have not seen. Let me leave you with one final thought, and then I will let you sleep. Throughout this descent, I have been telling you about prehistoric oceans as if they were a separate thing from our modern oceans, something that existed in the past, at a time that is not now. And in the surface layers, that is broadly true. The Cambrian surface ocean is gone. The Devonian sunlit zone, full of placoderms, is gone. The Mesozoic seas, where mosasaurs hunted, are gone. Those ecosystems have been dismantled and replaced over hundreds of millions of years by whatever succeeded them. But the deep in its essential character is not gone. The deep is the same deep. The water that fills the Mariana Trench tonight is, by its temperature and pressure and chemistry, effectively identical to the water that filled some Jurassic trench 200 million years ago. The deep is not a memory of the prehistoric. The deep is the prehistoric. Continuously. without interruption, in the same place it has always been. When you stand on a beach and look out at the ocean, you are looking at the surface of something ancient. Most of what makes the ocean is not what you can see. It is what is below. And what is below has been below, essentially unchanged, since before the first animal ever crawled onto land. This is the paradox I want to leave you with. We think of history as something that has happened. Events in the past, creatures that lived and died, ecosystems that rose and fell. But history at the deepest level is not always over. Some of it is still here. Some of the organisms we have talked about tonight are still alive, in deep water tonight. Some of the ecosystems we have described are still functioning, below our feet right now. The Cambrian is gone from the surface, but the deep-sea lineages that separated from the surface lineages in the Cambrian are still down there, still doing what they were doing then. In a meaningful sense, the prehistoric ocean never ended. It just retreated downward. And if you could, somehow, look through the ocean the way you can look through glass, you would see that the past is not behind us. The past is below us. Kilometers below, in the dark, in the cold, in the unbroken continuity of water. When you dream tonight, if you dream of water, let it be deep water. Let it be black water. Let it be the kind of water that holds things so old that calling them prehistoric is almost an insult, because they are not before history. They are the history, still in progress, still unfolding, still alive. Somewhere in the Pacific right now, a coelacanth is swimming. It has been swimming in some form for 400 million years. Somewhere in the North Atlantic, a Greenland shark that was born 300 years ago is cruising slowly through deep, cold water. It will still be alive when the person listening to this has been dead for generations. Somewhere in the deep subsurface, in rock 2 kilometers below the seafloor, a microbial cell whose lineage goes back 3 billion years is performing, slowly, the same metabolic reaction it has been performing since before there was oxygen in the atmosphere. These are not metaphors. These are not reconstructions. These are the actual, present-tense facts of the world we share with these creatures. The deep does not care about us. The deep does not know we exist. The deep has been there for billions of years, and it will be there after we are gone, probably essentially unchanged, still dark, still cold, still full of the quiet ancient things that have outlasted every extinction, every ice age, every rise and fall of continents, every rise and fall of the light. And that, perhaps, is the true horror and the true comfort of the deep. It was here before us. It will be here after us. It will never notice the difference. Think about that for a moment before you let the thought go. Every creature we have described in this descent, Anomalocaris with its 16,000 lenses, Camarosras gliding through the Ordovician twilight, Dunkleosteus shearing its prey in half, Plesiosaurus with a bite powerful enough to crush a car, the Mosasaurs hunting in the Cretaceous, the coelacanth hiding for 66 million years in a cave off East Africa, the Greenland shark born before the American Revolution. Every one of them shared something with every one of us. They looked at light, or at the absence of light. They felt pressure. They moved through water. They breathed or did not breathe, or found ways to extract energy from environments no human has ever visited. The oceans do not belong to any of these creatures, and they did not belong to the ones before, and they will not belong to the ones after. The oceans simply are. Life moves through them. Lineages rise. Lineages fall. Some lineages hide in the deep and outlast the surface, sometimes by hundreds of millions of years. The ocean absorbs all of this without remark. Every fossil on every continent is, ultimately, something that the ocean processed, preserved, then lifted into the light when continents rose. We are part of that process too. We will not always be here. The version of Earth that contains humans is a very thin slice of the version of Earth that has contained life. When this slice ends, the oceans will continue, and something will swim in them, and the deep will still be dark, and the things in the dark will still be waiting, patient as they have always been, for whatever comes next. That is the thought I want you to carry into sleep. Not as a fear, as a kind of peace. A reminder that the world is older and stranger and more continuous than the brief span of a single life can fully comprehend, and that beneath all the noise of the surface, there is a cold, quiet, enormous stillness that has been there always.